The equivalent capacitance of a series combination is always going to be less than any individual capacitor in that combination. We'll use the formulas shown here to calculate the equivalent capacitance of a series of capacitors. Series simply means that we're going to have one capacitor connected to another in sequence like this. It's different from a parallel type of situation. Now, in our problem, we have capacitors C1 and C2, which are 8 microfarads and 10 microfarads. We want to find the equivalent capacitance of the combination. Okay, so what we want to do is we want to replace these two capacitors with just one single capacitor, which we'll call CEQ. Okay, so let's connect our two capacitors in series to a battery. This is the real circuit where we have 9 volts at the positive terminal of the battery, 0 volts at the negative terminal, and we have C1 and C2. However, what we'll do now is replace that with an equivalent circuit of just one capacitor, CEQ. We'll still have the 9-volt battery. And let's use the formula above to calculate what this equivalent capacitance would be. The formula is 1 over C1 plus 1 over C2, and we could keep adding in more terms if we had more capacitors in series. We have an 8 microfarad and a 10 microfarad. So let's do 1 over 8 microfarads plus 1 over 10 microfarads. All right, so when you enter this into scientific calculator or graphing calculator, you want to do 1 over parentheses 1 over 8 plus 1 over 10. That would be an easy way to enter it. So see, our denominator here is in parentheses, so that'll get calculated first. And then we will do the division at the end. So it comes out to 4.44 microfarads. All right, so that is going to be the equivalent capacitance. Notice that it is less than either of the two original capacitors. And one way to conceptualize like why this is if we have two capacitors in series, then the distances between them are in series as well. So it's like having a larger gap in your capacitor, and the larger the gap is, the smaller the capacitance, the less overall charge it can hold. All right, now we're asked what is the charge stored on each of these capacitors. All right, so if we look at our equivalent circuit, we can figure out how much negative charge is going to leave the negative terminal of the battery. You could call it QEQ, for example. Okay, but notice that that really amounts to being the same as Q2. So whatever charge Q2 gets piled onto the negative plate of C2 is going to be the same amount of charge that gets piled onto the negative plate of our equivalent capacitor. So we can use the rule of CEQ equals Q total over delta V total. Okay. Now, we've determined that our equivalent capacitor has a 4.44 microfarad capacitance. We want to find out what Q total is, and we'll plug in the 9 volts of the battery. Now, how did I know to plug in the 9 volts of the battery? Because in our equivalent circuit, there's only one circuit element in there. We just have the single capacitor. So we're going to have a 9 volt potential on our positive terminal. So we're going to then have a 9 volt potential on our positive plate of the capacitor. Over here, we'll have a 0 volt potential, and we're going to have a 0 volt potential on our negative plate of the equivalent capacitor. So there's obviously a 9 volt drop across that equivalent capacitor. Okay, so I get that the total charge is about 40 microcoulombs. Okay. So that is how much charge is going to leave the negative terminal and pile onto the plates of our equivalent capacitor. And so that is also going to be Q2. Okay. Now, if 40 microcoulombs of negative charge piles onto the negative plate of C2, then it's going to attract positive 40 microcoulombs on the other side. Okay. This piece of metal in the middle is not connected to the battery, and it is neutral overall. So what's going to happen is if positive charge is drawn onto this side of the capacitor, then that will leave us with a negative charge on the other plate of the first capacitor. All right, now the middle piece is still overall net neutral, but it has become polarized. And so what's going to happen is it's actually going to put negative 40 microcoulombs onto the negative plate of C1, and that is going to attract positive 40 microcoulombs of charge on the positive plate of C1. So as you can see here, all the charges on the plates are the same, and that is common when it comes to capacitors in series. All right. We have one more question to answer. What is the potential difference across each individual capacitor C1 and C2? What we want to do now is we want to analyze the capacitors individually. Instead of analyzing my equivalent capacitor, I now want to just analyze C1 and C2 independently. All right, so we'll use the formula C1 is Q1 over delta V1. C1 is 8 microfarads. Q1 is determined to be 40 microcoulombs. And now we can solve for delta V1. It's 5 volts. And let's find delta V2. I get 4 volts. All right, so now we want to be able to label the potential values around the circuit because these become quite important when it comes to circuit analysis. So we've got 9 volts at the positive terminal of the battery. Of course, we have no circuit elements in between here and there, so we're going to still have 9 volts on our positive side of our C1. Now the potential difference across C1 is 5 volts. So we want to subtract that. Let's do 9 minus 5, and that'll give us a potential of 4 volts at the negative plate of C1. The metal in the middle will remain at the same potential, so we'll have 4 volts at that point. And then our delta V2 is 4 volts. So naturally, it's going to drop back to 0, and then the circuit is complete. And this is the type of thing that we're going to see when it comes to circuits, is that in an entire loop, you have to drop the entire voltage of the battery as you go through the circuit. Let's say we start at point A here on the negative terminal. Once we get over to the positive terminal of the battery, I'll call that point B in the circuit. And we're going to go way up from 0 volts all the way to 9 volts. Something happens chemically inside the battery to raise that potential from 0 up to 9. Okay, but once we get to this side, we're at a plus 9 volt potential. Now we're going to stay at that potential until we get to what I'll call point C here. So at C, we don't lose any potential. We stay at about 9 volts. Okay. At point D, we've jumped across the gap of the capacitor, and we're actually going to lose potential there quite a bit. We'll lose 5 volts, bringing us back to a potential of 4 volts at point D. And then we'll hold that potential for a little bit as we go to point E. Then we'll jump across the gap once again to point F. But when we get to point F, we've lost all the potential that remained, and we're back down to 0. Then we can go straight until we get back to point A and start the cycle all over again. This is called a circuit. And there's a loop involved. Okay. Notice that we added 9 volts, subtracted 5 volts, and subtracted 4 volts. So all of the potential that the battery gave us was lost in the capacitor elements that were found in this circuit.